Hi, today we are going to talk about how do we create custom graphs, something like this, within Ansys. Um, Graphs are very important element of an engineering task. We have a saying that a single picture can represent tens of paragraphs. Similarly, a single graph can represent tens of pictures as well, right? Let's say the single ACT command, we can bring up a GUI with graph which can be fully customized, even which can display the values as you see here. Okay, I'm going to briefly demonstrate how can we create this kind of custom charts using Ansys Workbench. The advantage of Workbench framework is that the Workbench framework is built on .NET framework. .NET framework is the basic platform for Microsoft to build the various programs like PowerPoint or Excel, Word, etc. One such .NET compatible language is IronPython. Ansys Workbench use IronPython as scripting language to automate and customize Ansys Workbench. If you go to Ansys installation directory, common files, there will be an IronPython folder which is installed by default whenever you install Ansys program on your computer. You could launch IronPython program from this exe. Whenever you draw any graphs on Excel through manual way, or you could create a graph in Excel using VB. Many of the engineers may be familiar with VB, but to draw a graph in Excel which is compatible with .NET framework, it is not necessary that you have to use only VB. You could use any .NET compatible program like C# or Silverlight and so on. So one such compatible program is IronPython. Using IronPython, one could generate a simple chart like this. So .NET comes with a lot of default assemblies which will enable you to create custom forms, drawings, data visualization. Chart is part of this data visualization. We could use this data visualization assembly to create a chart and add data points, and could add some legend series, then plot them. Okay, let's just read this file. I'm just going to read this. First I need to import my OS, then I'm going to execute this file which is in this particular path. What it is going to do is that it's going to bring up a chart which is nothing but a bar chart for data given here. Alright, so if you refer to MSDN, there is some good documentation about the various possibilities of using the charting assembly. So we are going to use this concept and extend it to do different kinds of custom graphs in Ansys. For example, let's take a typical creep analysis problem of a pressure vessel. This is a 2D axisymmetric section of a pressure vessel. Our objective is here is to do a creep analysis for 10,000 hours. This follows certain creep law, which is really not important for this demonstration, and it's having elastic plastic material property. Here the loading is time dependent. It is subjected to a cyclic pressure load like this, and the thermal load is also cycling. The way in which the pressure and thermal loads are cycling, not necessarily of the same pattern. Okay, it can be in phase, out of phase, etc., whatever it is. So upon the analysis, we could set up this problem, apply pressure as a function of time like this, temperature as function of time like this, and so on. Then we could solve this problem and look at how the displacement varies over time and so on. Now, this is analysis settings. Now we can plot the displacement and how the displacement varies with time, and we can plot equivalent stress. We need to produce so many graphs. Even Workbench by default gives us an option to graph this strain or stress, whatever the time is to variable. But it would be nice to have a picture, single picture like this, that contains the variation of pressure, von Mises stress, plastic strain, creep strain, total strain, elastic strain, temperature, and so on. Workbench also gives us an option to combine all these results like pressure, equivalent stress, strain, and so on. But we can't really plot the different scales in a single graph. It will get normalized. We can't really read what is the exact value of von Mises stress, what is the exact value of a creep strain. In fact, if required, we can bring up all the legends like this, but still we can't really read what is the exact, say for example, creep strain at this point. It gives just the normalized value. But if you look at this graph, at any point, say for example, of 1000 hours, you could read what's your total strain. It's around 7%. At 2000 hours, what's your say for example von Mises stress. You can read it from here and so on. Okay, so I'm just going to demonstrate a little bit on how we can do this kind of a stuff. Let's come back here. So whatever the script that we have, that for creating a basic bar chart, we could, as we did, create a custom graph with IronPython. We could do the same within ACT console like this. Say for example, see file and read that file exactly what I have, and you could bring up a chart. See, this is the chart, custom chart, and so on. Okay, all right. Having this as a concept, now we are going to first bring in the equivalent stress here. I convert that into MPa unit system because that's what I'm more comfortable with. Let me first read a chart which is going to produce time versus the 1 Miser stress. This is exactly nothing but I have a maximum 1 Miser stress like this, which is somewhere around 250 and varies like that, and the same is being produced here. Okay, so this is the very first part. Now let's see what are the various possibilities we can do that. After that, what we are going to do is that we are going to add a label which displays the maximum 1 Miser stress value for the entire time span. Wherever it is, it will show that value just below that point. Okay, now we can show additional curves on this graph. Say for example, let's bring in pressure and temperature values here. If you look at this, this is our 1 Miser stress, which is around um, 250, and this is my temperature graph. Okay, this is temperature around 450 here. If you look at the pressure is somewhere around 20, which is far below this range. It's around 20 range. Just to make the readability better, let's multiply this pressure by 10. Okay, so when we multiply this pressure by 10, the graph will go up and the readability will become better. Okay, this 21 will become 210, so that the readability is little better now. Now let us bring other strains, say for example creep strain, something like this. Let's bring the creep strain in this graph. For that, just going to bring in additional creep curve. See, this the creep, I have provided the marker just to distinguish this. Now notice this, all these values are in terms of hundreds, but the creep strain is in terms of e power minus 2. It's very difficult to show hundreds and e power minus 2's in the same graph. So what I'm going to do, we can move this creep strain into secondary axis, something like this. So I have brought in additional axis now. This is a primary vertical axis and the secondary vertical axis. So the creep strain is plotted in secondary vertical axis. This is somewhere around 0.06. Okay, that's what we are seeing now here. Now let's bring in name for the axis. What is x represents, what's the vertical axis, and so on. To do that, I'm just going to adding the axis. Say for example here my x-axis represents the time in hours and the y-axis represents stress or 1 Miser stress and pressure. Both are having unit of MPa, and also the temperature here. Okay, and the beauty is that you can drag and make it bigger and smaller and so on. See, now if you point to any data, it's not going to display a value. Okay, somewhere we have to add that. Let's see that. Now let's bring some title for this chart. So the chart title can be something like pressure vessel creep analysis summary. Okay, this looks kind of a nice graph. Now what we can do, we have a creep strain alone. Now we have a significant amount of plastic strain and something around 0.01, and we have very less elastic strain. Let's bring all these strains into this graph. We could get this data and bring these graphs something like this. Now if you look at this, this is a creep strain. I have also given an option to get the value x and y axis value. What other curves also you can see here. Okay, this is a very nice feature. You can just go and see the values here. So this is a total strain, this is creep strain, and this is plastic strain, and this is elastic strain. But at this point of time, it's important to give some legends for each curves. Let's give some legends for each curve. So it's going to look like this. Now we can identify the green is pressure, which has to be read here, and purple is a one measure stress, which has to be read here. P is a strain. Okay, this is blue is a plastic strain, and C dark blue is something like with a marker is a creep strain, and red is total strain, pink is elastic strain, and kind of orange is temperature. Now it's very clear. If you want to know exactly for any point, say for exactly here at 6,300 and 317 or 18, how much is the total strain? It's around 4.8 percentage. Okay, it's very visible here. Now there are two important quantities often we look at. One is the one measure stress, and another one is the creeps. Um, one is the one measure stress, that's a purple color, and another one is the creep strain. For creep strain, we have ordered some marker. Let me bring in some marker for one measure strain as well. One measure stress as well. So now if we look at these curves, so there are some markers for one measure stress and marker for creep strain. We have the maximum value displayed for one measure stress and the maximum value displayed for a total strain. Note that the maximum value can occur anywhere within the time point, not necessarily at the end. Say for example, one measure has happened somewhere in between. Okay. Now it is also possible to take an image of this graph into some external directory. I prefer to use something like taking an image of this in user directory of that particular project. Okay, now we could see that the image of this graph, whatever see in this GUI, has appeared here. And also what we can do that, I just delete this just for a demonstration purpose. When you are doing this kind of work with some kind of automation, you are running this in batch mode, you don't want to even bring up this custom GUI which displays the chart inside Workbench Mechanical. Once you have the script ready which exactly plots the graph in a way you want, what you could do that is you can just execute the script in the background, which is not going to bring up the GUI on your screen. Notice here in the solution tree I have no image here. Once I execute this, it's going to just insert an image here. That image displays your graph, something like this. Okay, we have multiplied the pressure value by 10 in order to improve the visibility. So it is also possible to label the pressure curve with pressure into 10, so that whoever is reading this graph can understand that this 210 really means 21 Pascal. So this gives you full flexibility to draw any kind of a graph that you can imagine you could draw in Excel. Okay, there are graphs like polar charts and so on. I will show you in coming demos. Let us look at another example for custom chart capability in Workbench Mechanical. Let's consider a plate which is of something around 50 mm height and which is having 10 mm radius hole. This plate is fixed at one end and it is subjected to a pressure, axial pressure on other end, and the whole center is subjected to a kind of a torque or moment. Because of this applied load, the structure is deformed something like this. Now, our interest is to calculate how much the circularity of this hole is changed due to the applied load. Workbench gives very nice feature to calculate the change in radius. Say for example, we could create a cylindrical coordinate system at the center. Then in the cylindrical coordinate system we can look at the x-axis, that's nothing but a radial direction. We could create a path and we can plot something like this. This is how the ovality of the circular hole. This is nice. But indeed, it would be very nice if we can plot this on a polar graph, something like this. Let's say um, this is a custom chart, just made something like this. Initially, it comes up with the hole radius, something like this, which is 10 mm circular hole. On top of this, what we are going to plot is this change in radius. Okay, we could in this custom chart, it's a custom GY. You could not only plot the graphs, you could add the buttons and assign some task to this button. When I click on this deformed results button, what it is going to do is that it's going to plot the deformed radius or the change in radius in terms of micrometers. Okay, we have a flexibility to manipulate the numbers here. Okay, look at this. This is very tedious to understand because the change in radius at some places, the radius is slightly on the positive side, the change in radius. At some place it's in the negative side, but in between somewhere in the green, it's the original radius of 10 mm. It's not changed. It's kind of difficult to get an insight from this graph. Rather, we could draw it on this graph and get kind of an insight. But however, even this graph is not giving a good insight because of the order of difference in the scale. Okay, this is 10 mm, the original radius, but the deformed radius is in some microns. Okay, so that's where the log scale come into picture. So once I convert this diagram, polar chart, into the log scale, and it becomes very evident to physically interpret the results. So this is the 0 degree where the x-axis points, and this is full 360 degree. The originally the blue color shows it's very nice to see this kind of things. 10 mm radius, and here is the deformed shape. Okay, this again plotted in micrometers. We could give a nice label for that. On top of this, I want to just understand how is my normal stress sigma xx around the hole. We could plot that on this path. Again, on the chart it looks like this, but it would be really nice to represent the same on my um, on my polar chart, something like this. So this shows the kind of variation. Okay, um, how this around the whole axis it varies. Okay, so basically the idea for me is to demonstrate workbench mechanical gives you the flexibility to draw any kinds of custom chart with different units and so on. As long as you have a logic, it's possible to implement that. And another example where these custom charts are helpful, or acoustic analysis. Say for this example, a typical muffler with porous holes and some kind of absorbing materials. We have done the acoustic analysis. We have got a pressure plot, and also we have got transmission loss plot. Let's say we want to plot this as kind of um, 1 by 3rd octave level bar charts, and want to calculate overall um, overall transmission loss for the entire range. Perhaps we could do a custom chart for the same graph that would look something like this. Okay, so here the same information, it's converted in terms of this is 1036 something that's here, and so on. Same information is plotted here. What we could do, we could use this script to calculate the overall um, overall level of the spectrum. Okay, taking the typical dB summation formula. Okay, these kind of things are really useful. I'm not really getting into the physics, just show what kind of custom charts you could create using ACT scripts. Here is another example for custom graphs generated in Workbench Mechanical for a typical rotodynamic problem. Basically, this is a rotating shaft sitting on a stator, or a kind of a support structure. So here the rotating part is modeled with beam and mass element here. On this mass really represent a disk. There is a unbalanced force. So we are calculating the response of this shaft due to the unbalanced force. We are tracking two results. One is the left end velocity, the other one is the right end velocity here. So we have two results like this, which shows information here like this. We could bring these two results together in some form here. This really looks nice, but for this system, say for example, this system is having a requirement that maximum velocity at the tips should be less than 250 mm per second. Okay, so somewhere here this is operating in certain speed range. Let's bring the custom chart first. So what it's going to do, it's going to bring this, let me show legend as well. Okay, the left end Vx, we could add another graph that will show right end velocity. This is having a limit of 250. We could just plot that. Immediately we can see that where the places it's exceeding. Now when we are talking about rotating structure, it's always convenient to have any response in terms of RPM, rather frequency. So I could add really another limit, something like here is my RPM corresponding to this frequency. This system is expected to operate maximum 15,000 RPM. Okay, this is my speed limit, 15,000 RPM, and my velocity limit is 250 RPM, and also my minimum operating RPM for this machine is around 3000 RPM. So I could really plot operating zone diagram, something like this. This is my operating range. Though in this region the velocity are really high than the permissible limit, we are not going to operate in this region. So this is not of our worry. Only a place where this exceeds is around 183. heads that corresponds to somewhere close to 11,000 rpm, and which has around 271 mm per second. Okay, so we need to make some design changes only to bring down this amplitude a little bit. Okay, I hope this gives clear understanding of various ways we can use custom charts to generate any form of charts that you wish. Okay, this gives you an ocean of opportunity to customize your Ansys charts. To do this, the code will typically look like this, and you can use it like mechanical APDL. You can just copy paste and do your result interpretation and take a image for your reporting purpose. Once you have the basic code developed once, then like in mechanical APDL, you can go and make further changes depending on the project, few variables, and use this for particular project. Hope this helps you to understand the basic capability of workbench customization. If you are familiar with Windows Forms, C Sharp, or IronPython, you should able to do this based on the first sample code that I have given. Initially, if you need any help, reach out for consulting options. Thank you for listening.